Have you ever wondered what Earth would be like if it had rings like Saturn? Of course you know that Saturn isn't the only planet with rings. Jupiter, Uranus, and Neptune also have them, although they're much less visible. But the main question that pops in our mind is why only gas giants have rings? What would happen if Earth had its own ring system? And what are the fascinating reasons behind these planetary features? To understand how we discovered planetary rings, we gotta go back in time. The first sighting of rings happened in 1610 when Galileo turned his telescope towards Saturn. He thought he was seeing giant moons around the planet, but Galileo was a dedicated scientist and kept observing. By 1612, those giant moons had vanished from view. Galileo thought that they might have moved behind Saturn, but he was actually seeing the ring's edge without realizing it. It wasn't until 1616 that his sketch showed Saturn with what looked like handles or ears. Then, in 1655, Christian Huygens, a great scientist, figured out that these were actually rings. As for the other gas giants, their faint rings were discovered much later. Jupiter's in 1977, Uranus in 1979, and Neptune's in 1984, thanks to the Voyager space probe. These rings are so faint that we needed a space probe to spot them. You might wonder if only gas giants have rings, but that's not the case. We've even found rings around dwarf planets. In fact, there's no reason a rocky planet like Earth couldn't have rings. In the next 30 to 50 million years, Mars's moon, Phobos, might even turn into rings. Rings can indeed come from moons, as well as comets and asteroids. There are various ways rings can form, but their stability is influenced by where they form around a planet. Moving back in time, the study of planetary rings advanced significantly in 1848 when Edward Roche introduced the concept now known as the Roche limit. This is the distance from a planet within which other objects form rings. Earth's moon didn't become a ring system because it formed outside this limit. Billions of years ago, a Mars-sized object collided with Earth, sending debris into space. This debris, still under the influence of Earth's gravity, came together to form the moon. If the debris had been closer to Earth, it might have formed rings instead. Predicting where this limit is possible, though approximate. For example, Mars's moon Phobos is expected to become rings in the future. To illustrate, consider Phobos and Mars, with Phobos' size exaggerated for clarity. The gravitational forces on Phobos vary because some parts are closer to Mars and others are farther away. This creates varying tidal forces across the moon. The tidal forces are the key factor, not just the total gravity. The differences in tidal forces across Phobos means that it will eventually be torn apart by these forces, leading to the formation of rings. But not all moons break apart because tidal forces are not the only forces at play. Understanding why requires looking at how these forces interact. Imagine a small rock on the surface of Phobos, specifically on the side facing Mars. This rock experiences a tidal force pulling it towards Mars due to the planet's gravity. If this were the only force acting on the rock, it would indeed be pulled off the surface and drift towards Mars. However, this doesn't happen, which means other forces are at work. One important force is Phobos' own gravity. Phobos, like any other large object, has their own gravitational pull that holds its material together. This self-gravity is the force that keeps the moon intact by counteracting the tidal forces pulling outward. For the rock on Phobos, there are three key forces to consider: the tidal force pulling it up, the moon's gravity pulling it down, and the upward push from the ground that keeps the rock in place. Currently, Phobos' self-gravity is stronger than the tidal forces from Mars, so the rock remains on the surface. But we said before that Phobos is going to turn into rings in the future, right? And that's because this balance is not permanent. Phobos' orbit around Mars is slowly decaying, meaning it is gradually moving closer to the planet. As Phobos gets closer, the tidal forces it experiences will become stronger, while its own gravity will stay the same. Eventually, the tidal forces will become so strong that they overpower Phobos' gravity. When this happens, the rock, and by extension, all the material making up Phobos, will be pulled away from the surface. This critical distance where the tidal forces become stronger than the moon's gravity is known as the Roche limit. The Roche limit depends on the mass of the planet, the mass of the moon, and the size of the moon. There's a specific version of this concept called the rigid Roche limit, which assumes the moon is perfectly rigid. In reality, this assumption is a bit of a stretch, as moons are not perfectly rigid. The forces involved can cause the moon to break apart if it gets too close to the planet. Roche took his ideas a step further by considering that a moon might stretch and deform before breaking apart, rather than being perfectly rigid. This adjustment led to what is known as the fluid Roche limit. When deformation is factored in, the Roche limit actually becomes larger because the moon can stretch and redistribute its material, leading to a different threshold for breaking apart. It might seem surprising, but a moon that isn't rigid actually breaks apart sooner. This is because deformation increases tidal forces, which in turn causes even more deformation. This creates a positive feedback loop where the tidal forces and the resulting deformation continuously reinforce each other, leading to an earlier breakup. Both the rigid and fluid models of Roche's limit assume that a moon is simply a collection of small rocks held together by gravity. While this might seem simplistic, it's a fairly accurate approximation in many cases, especially for larger moons and asteroids. In some situations, such as with artificial satellites in the International Space Station or ISS, molecular forces become significant. These objects are too small for gravity alone to keep them together, so they stay intact even though they are within their Roche limits. Additionally, some materials like ice have sticky properties. For instance, Comet Lovejoy managed to survive in 2011 despite being inside its Roche limit with the Sun. The comet's icy composition allowed it to hold together better than expected, demonstrating that different materials can affect how objects behave under tidal forces. The Roche limit is a key concept in understanding where moons can break apart due to tidal forces. For Earth's moon, this limit falls between about 1.5 and 3 Earth radii. This distance is much smaller than the moon's current distance from Earth, which is over 30 times the Earth's radius. Because the moon is so far from the Earth, it is safe from breaking apart. If the moon had originally formed closer to the Earth within this Roche limit, it might have shattered into a ring system. However, such rings would have long since disappeared by now. Planetary rings are not permanent features. They are made up of countless particles that orbit the planet, but their orbits are unstable. Over time, these particles slowly fall into the planet due to gravitational forces. Data from the Cassini spacecraft, which studied Saturn's rings, shows that Saturn's rings are relatively young. They are estimated to be between 10 to 100 million years old. Scientists believe that Saturn's rings might last for another 100 million years before they eventually disappear. The large moons of Saturn play a crucial role in keeping the rings stable, which makes Saturn's ring system more durable compared to others in our solar system. If Earth had rings, they would have vanished long before the advent of life on our planet. Humans would have never been able to see them. For Earth to have rings today, a recent and catastrophic event would be necessary. Such events could lead to dramatic scenarios which are far from ideal. In general, planetary rings form when an object such as a moon or comet gets too close to a planet. If the object's inside the Roche limit, the tidal forces become strong enough to break it apart, resulting in a ring system. Outside the Roche limit, moons can safely form and orbit around the planet without being torn apart. So what do you think? Wouldn't it be kind of cool if Earth had rings? Let us know in the comments below, and don't forget to like and subscribe.